We'll probably never know the full extent of how badly Soviet nuclear power was managed.
I sat before the world in Vienna and blamed those young men at the controls. I made no mention of the role I'd played in their ignorance. I did not speak out.
Valery Legasov's suicide caused shockwaves throughout the Soviet nuclear industry. Design flaws in the graphite tips of Chernobyl-type RBMK reactors were finally admitted to and changes hurriedly made.
But we do know that Japan's nuclear industry has seen a steady stream of fatalities. This does not happen in France. This does not happen in Germany. Over a 10-year period, United States nuclear power was responsible for a single fatality, from 2003 to 2012. A uranium miner died when a support beam collapsed. Because every single source of energy has caused at least one fatality during this period, and we know how much electricity was generated by each energy source, we can express how safe each form of energy is as a quantity of watts per human life. For nuclear power, because there was only a single fatality, we divide by 1. Almost 8 million gigawatt hours of electricity per human fatality. The next safest form of electricity is hydroelectric power. Hydro produced about half as much electricity as nuclear, for which 6 people died during that same period. Next is natural gas. We've all seen natural gas explosions on the news. Somewhere between 26 and 27 people were killed during that same 10-year period. It is a fractional number because the natural gas was dual use. Only a portion of it was for generating electricity. Now that we're burning fuel, we have air pollution to consider as well. 144 fatalities can be reasonably associated with the pollution caused by burning natural gas over that same 10-year period. Even with the cleanest burning fuel, air pollution kills more people than explosions. Natural gas gives us about 52,000 gigawatt hours per human life. The safest renewable is wind, about 21,500 gigawatt hours per life. Wind fatalities are due to maintenance. Just like nuclear power, this could easily go up or down depending on how the industry is regulated in the future. But there are a lot of turbines, all requiring regular maintenance, each one producing a moderate amount of electricity. To improve the watts-to-life ratio and try to make it as safe as nuclear power, it is reasonable to expect the cost of wind turbine maintenance to go up, driving up the cost of wind power. 27 people died maintaining wind turbines over that 10-year period. Natural gas comes out ahead of wind because it produced far more electricity. Solar is 2.5 gigawatt hour per human life. There are a whole lot of rooftop solar panels, and each one only produces a tiny fraction of the energy that a wind turbine does. Of all renewable energies, photovoltaic solar power is the least competitive in terms of price, but it also offers the biggest opportunity for improvement if panels can be made more efficient. Such an improvement in panel efficiency would also improve solar's safety standing, since more watts could be generated for the same amount of maintenance. In the United States, from 2003 to 2012, average number of watts generated per fatality is 300 gigawatt hour per human life. How is our average so much lower than any number we've looked at so far? Because of coal. Let's not forget electricity produced by burning coal. Coal mining killed 298 Americans over 10 years. Coal mining fatalities dwarf all other forms of accidental death in the United States. But the big numbers are in air pollution. In 1 decade, burning coal has killed over 130,000 Americans, largely due to the release of tiny solid particles that we inhale, causing respiratory illness. Burning coal also exposes us to mercury poisoning. This is how America's consumption of electricity kills people, by coal. Every other source of electricity is safer per watt. On the other end of the spectrum, no other source of power has the potential to meet all of our electricity demand with such a small impact on human lives, disrupted ecosystems, and future costs projected from greenhouse gases being pumped into our atmosphere. Nuclear hardware is shielded from the degrading effects of sun, wind, and rain. All safety systems are focused on a small area and a handful of highly trained individuals.
Nuclear has the advantage that the amount of energy sort of per atom is about a million times better than coal or natural gas. So you start with this huge advantage, and yet given the complexity of the plants and the things you have to do, you more than wipe out your million for one advantage. And today's nuclear plants are fairly expensive, at least the way they're built outside of China. They're pushing the state of the art, and they're standardizing designs and things like that. So nuclear is one of the directions that we should innovate in. Nuclear innovation stopped in the 1970s. We basically have this sub-design thing that was put into Shippingport for the first power generator, and we basically built 400 of those that are all kind of custom, but not in any interesting way.
What choices can we make today so that nuclear power can be even safer?
Very few people understand all the options that are available in nuclear energy. It's a complicated subject. It's a subject that is actually quite new. The first chain reaction experiment was December of 1942. My mother was a teenager in 1942. She's still alive and kicking.
This is the only part of the energy business that has anything close to a Moore's Law capability for improvement. We're still at the very early stages of figuring out how best to put that energy inside the atomic nucleus to use.
The heavy water reactor will use about 0.7% of the uranium's energy value, and the light water reactor will use about half of 1%. They both do terrible. At normal pressures, water will boil at 100 degrees Celsius. This isn't nearly hot enough to generate electricity effectively. So water-cooled reactors have to run at over 70 atmospheres of pressure. You have to build a water-cooled reactor as a pressure vessel.
The number one accident people worry about, pressure is lost. Water that's being held 300 Celsius flashes to steam. Its volume increases roughly by a factor of 1,000.
If you don't get emergency coolant to the fuel in the reactor, it can overheat and melt.
This is what drives the design of this building. So if this happens, all the steam is captured in this building.
Now, the reactors we have today use uranium oxide as a fuel. It's a ceramic material, chemically stable, but not very good at transferring heat. If you lose pressure, you lose your water, and soon your fuel will melt down and release the radioactive fission products within it.
So they have a series of emergency systems
designed to always keep the core covered with water. We saw the failure of this at Fukushima Daiichi. They had multiple backup diesel generators, and each one probably had a very high probability of turning on. The tsunami came and knocked them all out. And people sometimes say, is nuclear energy safe? And the first thing I say is, well, which one? Thousands of different ways to do nuclear energy. Let's say, is the car safe? Well, which one? I had the good fortune to learn about a different form of nuclear power, the liquid fluoride thorium reactor.
We can fully burn up the thorium in this reactor versus only burning up part of the uranium in a typical light water reactor.
It's not based on water cooling, and it doesn't use solid fuel. It's based on fluoride salts as a nuclear fuel. You have to heat them up to about 400 degrees Celsius to get them to melt, but that's actually perfect for trying to generate power in a nuclear reactor. Here's the real magic. They don't have to operate at high pressure. They don't have to use water for coolant, and there's nothing in the reactor that's going to make a big change in density. Unlike the solid fuels that can melt down if you stop cooling them, these liquid fluoride fuels are already melted. In normal operation, you have a little piece of frozen salt that you've kept frozen by blowing cool gas over the outside of the pipe. If there's an emergency and you lose all the power to your nuclear power plant, the little blower stops blowing, the frozen plug of salt melts, and the liquid fluoride fuel inside the reactor drains out of the vessel, through the line, and into another tank called a drain tank. In water-cooled reactors, you generally have to provide power to the plant to keep the water circulating and to prevent a meltdown. But if you lose power to
the lifter,
it shuts itself down all by itself without human intervention.
A staggeringly impressive level of safety, even if there's physical damage to the reactor.
Thorium is a naturally occurring nuclear fuel that is 4 times more common in the Earth's crust than uranium. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. Because the lifter is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. We could generate hydrogen by splitting water and combining it with carbon harvested from CO2 in the atmosphere, making fuels like methanol, ammonia, and dimethyl ether, which could be a direct replacement for diesel fuels. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced.
You can see that uranium-235 is like on par with silver and platinum. Can you imagine burning platinum for energy? And that's what we're doing with our nuclear energy sources today. We're burning this extremely rare stuff, and we're not burning thorium. You know, some people who are kind of environmentalists, and they say, listen, nuclear power is not sustainable. We're going to run out of uranium. Okay, I will yield that point to you if we're talking about today's nuclear technology.
In 2007, we used 5 billion tons of coal, 31 billion barrels of oil, and 5 trillion cubic meters of natural gas, along with 65,000 tons of uranium to produce the world's energy.
So I have a friend who's trying to start a rare earth mine in Missouri. Jim, how much thorium do you think you'll be pulling up a year? He goes, I think about 5,000 tons. 5,000 tons of thorium would supply the planet with all of its energy for a year. And he goes, and there's like a zillion other places on Earth that are just like my mine. It's a nice mine, but it's not unique. It's not like this is the one place on Earth where this is found. Every time mankind has been able to access a new source of energy, it has led to profound societal implications. Human beings have had slaves for thousands and thousands of years. And when we learned how to make carbon our slave instead of other human beings, we started to learn how to be able to be civilized people. Thorium has 1,000,000 times the energy density of a carbon-hydrogen bond. What could that mean for human civilization? Because we're not going to run out of this stuff. We will never run out. It is simply too common.